Okay, let's get started. Yeah. Okay, good. So excellent. So we had two lectures in the format of recorded videos. I hope you guys like that, and feel free to let me know if you have any questions. Okay. I will have another conference to go early in November, and I will also record the lectures beforehand, and you can watch that. And then and now we have some invited speakers in the November. So feel free to enjoy all those lectures. Okay, so in today's class, we will continue to talk about the diffusion, and we will give more examples of diffusion. Now, in terms of the logistics, I only have one thing I want to update to you. Actually, it's the more elaboration of the updates. Okay, that is about the midterm exam and actually final exam. So for the midterm exam, we already discussed that you will present your final project's idea for the first time in the midterm exam number 2. And then you can do it individually or collaboratively for 10 to 12 minutes, right, for each group. And I have already put some examples into the canvas, but that examples mostly are the final report. Okay, so we will stick to this plan to proceed for the midterm exam number 2, and all of you can start to talk with me about which project you want to work on, and then I can help you to refine the project, and I can provide you new references that help you to enrich your project. Okay, ideally those projects should be the one that you love to do, you have a passion to do, and also it can be the project you're currently working on in your lab. Okay, so using this chance, you can enhance your understanding and then broaden your horizon on the field that you are working on, right? And then we can hopefully through this class, you can also develop a new method or new tools to understand the questions you are working on better, right? Good. So today I want to explain a little bit about the format of a final project. And the final project contains two things. One is the presentation. That will be in the final presentation, you will present the enhanced version of your presentation in the midterm exam number 2. And also you will write a final report to summarize your final presentation. Okay, so you will have in the midterm exam, you will only need to present 10 to 12 minutes for your project, give the background information about your project and your current ideas, current goals. And then in the final project, that will be December, you will present the enhanced version, as well as submit a final report. So today I want to briefly explain to you what is the final report looking like. In the canvas, in the sample, excellent example, I actually put some good examples of final report. Okay, so let me briefly explain that to you. Do you guys hear me?
Yeah.
Yeah. Okay, good, very good. Now, so let's look at the big picture. So in our class, overall, your final score will be consisting of those components, 5 components, right? So class attendance, you have no problem. Homework, you don't have any problem. This is a very good chance for you to practice the understanding of the concepts, and also the MATLAB programming is very, very fun. Okay, so enjoy those questions. And then we have two midterm exams. First of all, you guys all did very well. I look at your answers that you guys did very well for the 10 questions. All of you did a great job, so that's no problem. Now, for the second exam, which will come at the end of this month, then this one, you will present the 10 to 12 minutes about around that time, and then you will present the topics you like to do from the end of October to the beginning of December, right? So you will do that project Then this presentation, you can start to prepare now. And I can help, you can meet with me on the Zoom or in person. I can discuss with you to refine your topic, to help you select the topic, okay? And then you can prepare this presentation. After that, you will make the further deeper study of your topic, and then prepare for the final presentation, which is actually here, which is this one, final capstone project. Then you will present it on December 4th and December 6th. Okay, so this version will be the advanced version, deepened version of midterm exam number 2 version. Okay, then you will prepare a report, final proposal, final report for this project. Actually, it's the report, final report. Okay, and then that will talk about that will be before December 8th. Then you can submit it to me, email that to me. And this one, I have the example in the shared folder in the Canvas. You can use that. Okay. Now, regarding the last 2 points here, these last 2 points about the final project, I will explain it one by one. First, I talk about that based on the weight. Let me talk about the final project, 30% one first. This project, I hope you are not just doing a literature review, not just a review of existing literature. You also do an in-depth analysis. Okay, so you choose a biophysical problem that you have a great passion, and then you do an in-depth analysis of that problem. This analysis can be either that you propose a new experiment or new approach. Within 1 month, you may not have time. You may not have enough time to do experiment in a lab, although you are very welcome to do that, but you may not have time. So then what you can do is to propose one experiment that can help you to understand better or tackle this biophysical problem. Okay, and then you design this experiment, choose correct technology, explain the reason why you choose that technology, and explain the steps of experiment, and then provide the backup plan if that experiment does not work. What other alternative solution you may have to help you solve this biophysical problem. Okay, so this is a great approach, first approach. Second approach is you can develop a mathematical model, new physical model, just like what we did. That when we look at what we explained in the class, we see the Brownian motion of the particles, and then we explained how to model it, mathematically model it in the 1D, right? And then how to derive the equations to describe that random motion, right? And then that random motion, that model actually is underneath both the working of drunk man and as well as the movement of particles in the water. And actually, it also underlying many other physical phenomena, right? So what you do in this project is the same thing. If there is a phenomenon you are very interested in, phenomenon, and then you can develop a mathematical model to explain that physics beneath that. Okay, so the problem itself, phenomenon itself, can be the things from the cell biology or molecular biology. Okay, so this will be very fun to help you to train yourself to quantitatively think about that problem, not just the terminology. Okay, in the biology, if you open any biology book, there are many terminology, huge amount of terminologies, but that's just the name. What you want to know is the underneath physical laws, physical principles that are governing this phenomenon. And that phenomenon is nature will not tell you that. Nature just show the phenomenon, and it is our job as a scientist to model it, to interpret that phenomenon using mathematical languages. Right. So in the previous several lectures, we gave multiple examples about the mathematical languages, how to prove the things, right? How to describe things, how to prove things, and how to validate the things. So now it's your turn. identify a phenomenon and then develop corresponding models. It will be a great adventure for you. Okay, it can be wrong at the end of the day. That's fine, but the process you get excited, and then you continuously refine your model. And at the end of the day, the model can explain the big picture of the phenomenon. That would be great. Okay, in the numerical simulation field, there is a saying that every model is wrong because model is to capture the key parameter of a phenomenon and then use mathematical equations to describe that. However, it can miss many things. Okay, depending on the things important or not, it can miss some secondary factors. That's why the model is not correct, not comprehensively capture everything. However, all the models are wrong. Some of them actually are useful. It can help us to understand the phenomenon better. And also, more importantly, it can help us to predict new phenomena that follow the same physical principles. Right? So your efforts here will be very valuable, and it will be a greater practice, great exercise for you to do this final project. So enjoy it, okay? And also the project you propose should be your own idea, okay? Fresh idea, should not be already existing in the published literature. Holding a torch into a darkness and then find something new, okay? This whole experience is very useful. Can you guys hear me?
Yep, we hear you.
Yep.
Excellent. So this is the principle, okay? This is the goal of this project. Now, the presentation, when you make the final presentation, it will not be only a report, okay? Not a report to see the existing things, the existing knowledge, but also contain your own quantitative calculation, so that you do your own calculation, or either analytical or numeric, right? Either way, there are so many different software you can do the numerical simulation, numerical calculation, FEM, finite element, or molecular dynamics, or the other kind of simulations, boundary element methods, and many other methods, right? So you choose the correct method. We don't care whether the method is fancy or not. We care method is appropriate or not. Okay, and then use that to do the quantitative calculation on the problem. Okay, and then show that clearly in the presentation. Explain your logic, explain your results. Okay, even the results may be very preliminary, but it gives us the very fresh insight of the science. Okay? So that would be excellent. Okay? Now, this will be the final project, and then after the presentation, you can write a report. That's a separated grading, right? Write a report, and then in the next few slides, I will show you how to write what are the components of the final reports. Okay, and here is the format. 5 to 8 pages should be fine, and contain figures content figures. That's the final report. And then for this presentation, final presentation can be 12 minutes oral presentation. Okay, and we have 2 minutes questions. Overall, both the written, which I will explain in the next few slides, and the oral together will be 30% plus 10% for your final score. Okay, and the final grade actually will based on the scientific value, scientific value of your presentation, of your work, and the presentation quality. How good are you to convince the audience? The audience will be all your classmates, right? So you need to make sure all the classmates understand what you're talking about, and then be interested in your topic, right? So your contents matters, your presentation matters, and also use of the relevant course topics, and the validity of your quantitative calculation matters. Whether this makes sense or not, whether this is really relevant, really relevant to class, right? So based on this, you will get the final grade. So let me explain to you a little bit about that report, this report. So, some of you may not be familiar with how to write a report, and I want to explain to you the details, the format in just a few minutes, really briefly. Okay. So in our class, because you don't have sufficient time to really do an experiment, so this report is more like a proposal, lot more like a proposal. Okay. So this similar thing, you basically in this proposal, you want to explain three things in a very convincing manner and with sufficient supporting data, supporting evidence, supporting literature, okay, towards one scientific question. And then in this proposal, you want to explain basically three things. Firstly, you want to explain to people what topic you will choose to study and why that is important. Okay, which topic? First one. Second one is towards that topic, what exactly you want to do? What's your goal? Usually in the proposal is called a specific aim. Towards the goal, what a specific aim you want to achieve so that it will help us to understand the topics better. Okay. So what do you want to achieve? Specific aims. And then thirdly, how you will do it. What is the experiments you designed towards that goal, and how do you implement those experiments to achieve those goals? Right? So that's the third one. And also in the third one, you also include what's your backup plan. If the experiment that you proposed turns out not working, that always happens in the lab, right? So then what's your backup plan? You can still choose another route to help you achieve the goal. What are they? You need to elaborate them very carefully in the proposal so that people believe, okay, this is you indeed have thought through the whole scientific question solidly, and then we believe what you proposed, and we are excited about what you proposed. We look forward to your success in implementing this project, right? So that's what you want to deliver inside this proposal, okay? In writing, in the final project presentation, you also need to deliver that in the same way, but in the PPT format, right? So that's the goal. Okay, now here are a few formats about the final report. Okay, you can just follow this. This will help everybody keep the same consistent format. It will be very useful. Okay, and then the grading about this written proposal would be 50% about the question. As I said, why this question is important, and what's your new hypothesis, your new idea. Okay, and then a bit about the background research, what have other people have achieved, and then now it's the experiment proposal. What is your approach and your discussion and how you interpret your data, right? And then the final 10% will actually be how you write these things, how you explain the three components I mentioned there, how you structure your project, how you illustrate and write whole proposal in a clear scientific with a clear scientific language, right? So that's the criteria. This is actually very standard criteria. If you apply for any fellowship, any student award, you need to prepare similar, and the evaluation criteria is very similar. So this project is a good exercise for you to apply to prepare for your future award applications or fellowship applications. Okay? And then this is the criteria. Now in the proposal, you can include 7 components. First is abstract or summary, project summary, okay, about 300 words. And then background and significance. The third one is specific aims. Usually you can propose 2 aims, 2 to 3 aims. nobody will propose just one aim. Okay, and because one aim is very risky. If that aim doesn't work, then what can you do within that time period, right? So usually propose 2 or 3 aims. They are independent from each other, and any aim, if it's accomplished, you can gain new knowledge, you advance the science. Okay, I will explain them in more detail in the next slides. And then number 4 is approach and method you will use. Give some explanation of those methods, and then explain how you will implement those approach and methods. And then number 5 is discussion. This will include alternative method, and then what the results you expect to get, and how you plan to interpret those results. Okay. Number 6 is go beyond this project. You show what future direction you can do if this project is finished. What other new things can this project lead to? Right. So this gives people a vasta for the future, right? A landscape for the future, right? So this can be short, just one paragraph, but it will be fun to write, so that the whole project is not just a one stop. It actually is an effort to open the door for the even bigger field, and then for the bigger field, people can start to propose new things to do to expand the current knowledge domain, right? So and then push the boundary, push the envelope boundaries, right? And then finally, you put all the reference, what all the things you discussed in the proposal or in the final report. Anything from the literature, you should reference that. We need to respect previous scientists, their efforts to provide the good, important knowledge foundation for all of us, right? So make sure we reference that and then list all the name of the authors, right? Now, for each components, I have a very few explanation for each one of these 7 components. Do you guys hear me? Yeah, excellent. Ask me if you have any questions. Okay, this is a very good practice for you to practice writing, practice thinking scientific question, practice convincing people by your presentation. Okay, in the future, when you become faculty members or the leaders in the national lab, you will need to do this again and again, because you need to convince people what you are doing is really worth it. It's really deserving the investment, deserving attention. Okay, so those are good scientific questions you are working on, and they have impact for the global society. You need to convince people honestly, but also effectively. Okay, so this is a good practice, very good practice for you to learn this, and then you can implement for the future. Now let me explain each component here very briefly to you. Then we get to our class topic. Now, for the abstract, first of all, abstract, no more 300 words. Okay, so abstract is actually the concentrated version of your whole proposal. Each paragraph in a proposal can be concentrated into one sentence, and then they can be linked together to form an abstract. Okay, that's the first one, very important. Usually people write it at the beginning. You think through the whole project, know what structure you will lay out first, and then write the abstract, condense the abstract, and then follow that abstract, lay down, expand it to each follow-up components. Okay. Second one is the background and the significance. So here in this section, you need to to be effective, we need to explain the importance, the significance of the problem, and the proposed project you are working on. What are the project? Why this project is important? Why in this project you want to address this kind of question? Why? Okay, so you need to explain that. And if this problem can be resolved, why they can benefit the society, you need to explain it very, very clearly in the first sentence, and in a language that everybody can understand. And the sentence cannot be too long. Every sentence 10 to 20 words, so that they can be very concisely deliver delivering the important message, most important message to the readers. Okay, so explain this importance. Okay, and then yeah, and then actually this contains what I just explained, how the proposed project improve the scientific knowledge in the biophysics and science. Yeah, this our class is the biophysics for engineers, right? So we are not talking about the biochemistry. We are not talking about the psychology, although those fields are great and very important. But here we are talking about the biophysics, right? And engineers, right? So you make sure focus yourself in explaining why the project that you propose will help those fields, okay? And then describe how the concepts and the methods that drive this field will be changed if the proposed aims are achieved. Means this actually is specific to the point I mentioned, that is the first method. So if you want to propose some new technology, new method to study, to tackle a scientific question, then you need to convince people why this new method that you propose, if they can be developed, why that can drive the field forward. In other words, why they can shift the current paradigm. Currently, people use a conventional method, but that method, the conventional method, may contain some limitations. Although they have very good, very clear strengths, but they may have some limitation there. And then you propose new method to be complementary to the conventional method. And then if that new method can be really achieved, can be realized, then how that new method can drive the field, you need to explain that very clearly. Okay, that is your significance, right? So in this section, make sure explain the background and significance very clearly. Number 3 is the specific aims. We get to the specific items. We need to propose 2 to 3 specific aims, and each aim will state concisely the goal of the proposed project. Okay, and then if that goal can be achieved, what is the expected outcome? What are the expected results? Okay, that results including the impact of the results, and also the meaning of the results, right? And then in this section, you make sure list succinctly the specific objective of the research proposed. What is your hypothesis? How you will test those hypotheses, and what is the specific problem? How you resolve the problem, and what's the current existing paradigm, the practice people use, and then how your method will challenge that existing paradigm, will revolutionize the current field. Okay, so this has to be explained clearly in the specific aim. Okay, this has a little bit of overlap with the section 2, background and significance, but the difference is background and significance section 2 is in a more broader picture. You talk about the field, okay, of the topic. The specific aims here, when you talk about the significance, actually is targeting to specific steps you will do, research you will do in this project. What's their significance? Okay, so they're the bigger, and one is bigger, one is more specific. Number 4 is actually very concrete. We talk about the approach and method, overall strategy, methodology, and analysis you will do to accomplish those aims we proposed in the section 3, and then including any data, the data, how the data will be collected, analyzed, and interpreted, right? So this is the very practical things that you will do if you perform this project. And then because no experiment will be completed without a failure, right? No experiment will be going very smoothly. We always people say that first experiment always fail, right? First several experiments, and then we learn from a failure. From those are, we call it a constructive failure, right? If your experiment is so easy to be successfully accomplished, then its meaning may not be that big, right? So that success is sometimes is meaningless or non-significant success. non-significant success. Okay, what we want is we want the constructive failure more. We like that because that will teach us to how to design next experiment. We do not like to get those insignificant success. That won't teach us too much things. That's just incrementally move on. That's not that useful. Okay, we don't want that kind of success. We want the failure. We want the constructive failure. Okay? Now, because we will get a constructive failure, then we need to discuss the potential problem, potential failure during the implementation of the project. So then we discuss that, and we also propose alternative strategy, how to learn from those failures. How can we develop a different route to achieve the goal, achieve these specific ends? Okay, so explain those, and then also during the research, we cannot. It's not good to find out the failure at the end of the day. We need to find out the failure quicker, so that we can design the alternative. We can implement alternative approach, or even design new strategies to correct mistakes quickly, right? So then you need to propose benchmarkers throughout the path to what's the quality control that can help us to check we fail or succeed. We need to do that. And then if it's successful, then what's the benchmark there? What is the criteria you can use to evaluate this success? Okay, then we can go to next step. So those is very detailed items. Every sophisticated research should think about. Okay? So research actually is like doing those research projects is like learning a business. You need to make sure that all the strategies are well thought through before you touch the project, before you start. And then all those strategies should be developed or considered within the correct scientific principles, in our case, correct biophysical principles, right? And then after this considerate thinking, then we can start the project carefully, right? So that's number 4. Number 5 will be the discussion. Once you get the results, how we are going to interpret it, how we will interpret those results, right? What are the results? What will the results tell us? Tell us the science, okay? And how, yeah, and also we need to discuss how those results will inform our new understanding in this biophysical problem you choose at the first place. Because not all the readers are from the same field. They may not understand the problem. So you need to educate people. What kind of new understanding we can achieve from the results you obtain here. Okay? So you need to explain that. And then number 6, future directions. This is what I explained earlier. Okay, I will not repeat that. So this will explain what is the new field you opened after the accomplishment of this project. Okay? And then finally, include all the references. Okay? So that's the format for the final report. In fact, you can start to prepare this report now. You can prepare this along with the PPT together in parallel. One is the presentation slides, photos. Another one is the text, more very rigorously lay out the 7 components I mentioned here to help you organize the resources, organize your time. Okay. Okay, that's all for the final projects. I think and I think you guys will do very well. Just make sure to practice it and let me know if you have any questions. Okay. Any questions? It's clear, right? It's clear.
Yeah.
Excellent, excellent. Now with this, you can start to work on that, and let's continue our class discussion. Okay, now from the previous classes, we have finished the mathematical derivations of the random walk. And we talked about the central pillar, one of the central pillars of statistical physics, the central limit theory, right? Now is a time we step into this field deeper and then talk about the diffusion, correlation, and more applications, and use those knowledge we learned to explain the phenomena we observed, right? For a biological problem, both in health and in disease. Okay. Now let's start to talk about the diffusion. So last lecture we actually briefly touched upon this material already. So we talked about the number, each step is delta t. For total time is t after n numbers of steps. We talk about that. And then for each small step, it can actually also be composed, each small step delta t can also compose to many even smaller steps, right? Then for each small step, it can satisfy the diffusion equation, mean MSD equals 2D delta t. And then this, because this is 2, right? This is the parameter is 2. That means it's in a 1D condition. And then all these things together, they can be composed. Yeah, okay. So here we also talk about the variance, and within that single step, it will follow the Gaussian distribution, and then put all the things together. We can form the final quantitative equation of Gaussian distribution. That the n steps, n number can be converted into a t, right? So then the Gaussian distribution is written in terms of the time, the evolving time, right? And then within it, we can also, within the Gaussian distribution, we given any Gaussian distribution, we will know what is its variance, what is its mean value, right? So from here, this actually we discussed previously, right? In this equation, you can see the mean actually equal to 0. Mean is 0. So that so that's minus x squared, right? But the variance is not 0. Variance is 2dt. Yeah, 2dt. So in the future, this is actually most important, one of the most important equation in the fundamental physics. Okay, so once you see this equation, you can quickly know the important parameters of this process. Okay. We also talk about the 2D case, 3D case, right? So that's a 4dt, 6dt respectively, and also we explained the meaning of those these particle trajectories in last lecture. We discussed about one application in the bacteria. So if in the bacteria there's a protein that will diffuse, given the typical diffusion coefficient of protein in the bacteria's plasma, which is 0.25, 1/4 of micrometer square per second. Given this, for the bacteria that of the size 1 micrometer, this protein takes only 2 seconds to go from one end of bacteria to another end, right? So we talked about this in last lecture. And then remember that equation we derived, that MSD, which is the delta S square mean, so the distance is square, equals to 2dt, 4dt, or 6dt. So in the left-hand side, distance is square. On the right-hand side, time is linear. Then if the distance increase, for example, the bacteria expanded. Now this bacteria, due to osmotic pressure, it becomes expanded to 10 micrometer size now. Then that protein is not that easy to travel now. If it still takes the diffusion process, okay, still take this, use this option, then the time becomes 200 seconds, more than 3 minutes. So then that's not really convenient, right? So they need other means to make this trafficking of protein to be more effective, right? So here is talking about the protein inside the bacteria. But if you look at the bacteria itself, because bacteria is small, it's so small, they can also perform random walk in the water, because they are also subjected to the thermal powered bumping of water molecules, right? So the bacteria can also do the random walk. But in the same time, bacteria has its own active mode. They have the flagellae at the end. So here in this picture, this is actual bacteria. At the end of bacteria, they are flagella. This is they will rotate. They behave like a motor to drive to propel the bacteria forward. Okay, so bacteria actually has both mode, both random walk as well as the biased random walk. We call it biased random walk. So it can go in a directed manner. Okay, so Professor Howard Berger, he is actually the leader to study the motion of bacteria in the nature. Do you guys see my mouse?
Yeah.
Yeah. Okay. Very good. So, Professor Howard Berger, actually, he's the first person to study how the bacteria move in the nature. He found that in his lab, I actually visited his lab many times. His lab is the neighbor of our lab previously at Boston, in a Harvard campus. So in his lab, he firstly used some glass capillary containing some chemical. Usually, that chemical is the food of the bacteria called attractant. Okay, such as aspartate acid, which is showing the molecule showing here. So he put the capillary in front of some bacteria, and then those liquid, those nutrient will diffuse into a liquid and then generate a gradient, and then bacteria actually will sense it. The reason bacteria sense it is actually the topic. Is the topic Dr. Berger was have been studying for his whole career life. Okay, so once the bacteria sense it, then bacteria will go towards the capillary, and then they will use those flagella to drive them towards that. Okay, so in actually early 1980s, Howard analyzed this problem. He developed a microscope that can automatically track the motion of a single bacteria. Okay, and then he find the bacteria actually under that situation, this chemical sensing situation, bacteria can perform a biased random walk, and then they can swing in a straight line. Okay, they never do the random walk when the food is present distantly. Okay, then they can also the speed achieves 14 micrometer per second. Okay, very, very quick in that micro scale. Remember, in the micro scale, water, if the size, bacteria is 1 micrometer. If you reduce the size from centimeters to the micrometer, you actually enter a very different water in the liquid. The viscosity of the water cannot be ignored anymore. Okay, you have the low Reynolds number, and then that means the initial of the movement becomes not ignored, cannot be ignored. Okay, so then bacteria actually need to perform very hard work to rotate its flagella to move forward. Okay, so this speed, 14 micrometer per second, is actually a very large number for bacteria in that size for this entity. Okay, and then he also find many interesting behavior of bacteria, like random tweeters, and also start off they can also tweeters. They can do the tweeters and then change the direction. How they bacteria quickly change their direction based on the condition. Okay, so bacteria actually is although bacteria does not have eyes, they have a way to sense the environment, to check the food, and then make a decision where to go. If there are 2 nutrient sources there, they can make a decision where to go. Okay, so all this process are captured by the microscope built by Howard, and then by analyzing those behavior of bacteria, he achieved a lot of new understanding about the biology and biophysics of those microbes. Okay? So he actually write a very, very nice book. This is a very, very good, very thin book, not a thick book, called Random Walks in Biology. You can read this book. I have the electronic version. This is a very, very good book. If you read this, you will understand how the microworld looks like. Okay? This is a very, very good book. And then I think I show, and then what he observed in the microscope, actually I showed you previously in the video. So something looks like this. There's the circled entity is a bacteria that swing persistently, rapidly towards the food. Okay, and the other bacteria, they are moving in different directions because there are multiple nutrient sources present in this tank. Okay, so and also some bacteria you see here is rotating, right? I mentioned this before because the bacteria is thinking which resources they should go. Some of the resources on the right hand side, some on the left corner, right? So they are deciding which one they should go. Okay, so their behavior is very different compared to those small dots. Small dots are fluorescent beads. They are doing a random walk. They are in a very equivalent way, right? They're in an equivalent state. But the bacteria is in a non-equivalent state because they are consuming the ATP free energies, and then they make the persistent movement towards one direction, right? So this actually is the one video captures the diverse phenomena in the micro world. Now, now more things about what Howard discovered is he also find when the bacteria swing up a concentration gradient, they were less likely to twitter because the food is in front of them, and then they move when they swing, the concentration of the food becomes stronger and stronger. They are against the gradient, right? So they are less likely to twitter because they don't need to think about the other things. Now they just go for one target to get the food. And then, but if they swing down a concentration gradient, then they are more likely to twitter because the food concentration becomes less and less. Then their mind get occupied by the other attractions. There are other food sources. Then they start twitter and then start to do the cognitive thinking, right? So,
right, Dr. Tang, in the video you said that the bacteria was moving towards the food.
Yeah.
But why weren't the other bacteria in the video also moving towards the food?
Excellent. So I actually explained it in the previous few minutes. I'm saying that in this field there are multiple food sources there. You see those bacteria, they're actually in different folds. This is not a 2D. This is in a tank. This is a 2D, a 3D. This is in a 3D. Some of the bacteria you see the smaller, and they have a ring around that. The ring is because we are out of the focus. Okay, the light is reflected. So in the whole 3D world, there are multiple food resources, and each resource has a gradient in a certain range, right? So this bacteria sends the food on the right hand side. Some other bacteria sends the food in the left corner. Then they go to the left corner, right? Yeah, yeah. Very good question. Yeah, good. Now what Howard discovered here actually is not very obvious at his time, in the 1980s. It's not very obvious. Okay, so he finds that the distribution of the step size become biased towards the higher concentration of chemoattractant. Okay, and then the bacterial model is in quantitative agreement with the distribution of bacteria around the sources of attractant. Okay, and throughout Dr. Berger's career, he actually investigated heavily into this problem, into this question. Okay, and then his study is on how the bacteria know whether their life is getting better or worse, and especially also how the bacteria remember things. Bacteria actually can remember if they have been close to one nutrient source. They will know that once that the nutrient source is used up, after many years, they will still go to that place. They will think that place still have nutrient. So they know, they have memory there. It is not known where is the memory stored in the bacteria. Where is memory? Just like human. our human being also have memory, but we still don't know where is the memory in our brain, right? Our brain is not like the hard disk. In the hard disk, you can put in the data. In the computer, you can put it in. But in the brain, where is our memory? Okay, so where is our memory? Is it in the neuron cell, or in the astrocyte, or in the extracellular matrix? Where is that? That is not known. In bacteria as well, bacteria can remember things. Where is the memory in this single cell? Where is the memory? It's not known. Okay, so those are very hot area people right now are working on, and Dr. Berger's work actually laid down the foundation for this field. Okay, so Dr. Berger actually has a series of lecture online. Actually, I put the link here. You feel free to watch. Here is the one experiment he's explaining. You see different pattern here, right? He is explaining that if the people did the experiment with different sources of nutrient. Here you use the oxygen as a source. So he explained different patterns can be generated when the source, the nutrient is designed differently in the experiment, right? So you can feel free to watch those videos and then learn more. Okay? So he is actually the leader of the biophysics to connect the micro world, microbes biology with the physics underneath it. Okay, he is not a biologist; he's the physicist. He used the physics theory to understand better the biology in the micro world. Okay, good. So this is in the bacteria. Now, if we apply the same principle to larger cell, for example, we have a neuron. We in our body we have we are eukaryotic. We have eukaryotic cells, right? We have eukaryotes. Those cells actually have a larger size. Okay, larger size. Remember in the previous lecture when I showed a picture of cancer cell, it's 20 micron, 30 micron, that size. And in fact, in the body, we have even larger size cell, like in one dimension, like the neuron. They can be meters long, right? Meters long. In the bacteria, if it's only 1 micrometer, protein would take 2 seconds. And if 10 micrometer takes 200 seconds, then if in the neuron is a meters scale, then it will take a very, very long time for the protein to traffic to its destination, right? That is not designed, not efficient for us, right? We wanted the neuron to work very quickly so that we can think quickly, we can react quickly. Those long neurons in our body actually help us to quickly react towards the external stimulation. If you touch a hot coffee, there's a hot cup of coffee. Once your finger touches it, you want to quickly retract your hand. You don't want to hold your hand there, burn your hand, and then after several minutes, you realize it's hot. That's too late, right? You want to quickly retract your hand. So you want to do things very quickly. Then means diffusion is too slow. It's not an appropriate option for this kind of eukaryotic cells function, right? So in this times, eukaryotic cells take other options. There are several options. One is motor protein. Within the eukaryotic cells, such as neuron, there are many motor proteins exist. They can run quickly around the cytoskeleton. Secondly, many neuron or many other eukaryotic cells, they don't rely on the trafficking. They can invent new organelle in situ and quickly localize the biomolecules in the subcompartments. Okay, they can. Oh, our time is up. So it's 3:55. Okay, we can continue our class in next lecture. I don't want to delay you guys, so you can go ahead for the other things. Then let's continue in the next lecture. Okay, thank you guys.